Dear students, in last class we studied ideal frequency response of linear phase FIR filters. In today's class, we will study the different techniques for designing linear phase FIR filters. There are three well-known methods for designing linear phase FIR filters. First one is Fourier Series method and window method. Second one is frequency sampling method. And third one is optimal filter design method. As per your syllabus, you will be learning first two methods only. And the third method you will not be learning in this subject in your class. We have studied that the frequency response of a digital filter is periodic with period equal to 2 pi. And in signals and systems subject you have learned from Fourier series analysis we can express a periodic function as a linear combination of complex exponentials. The frequency response of a digital filter is periodic with periodicity of two pi. This fact we have studied previously while designing the IIR filters. And in signals and systems we have learned that from Fourier series analysis any periodic function can be expressed as a linear combination of complex exponentials. Therefore, the desired frequency response hd of e raised to j omega, which is periodic with a period of 2 pi of an FIR filter can be represented as a linear combination of complex exponentials using Fourier series. That is, hd of e raised to j omega is equal to summation from n equal to minus infinity to plus infinity hd of n into e raised to minus j omega n. Let us call this as equation 1. Where the Fourier coefficients hd of n are the desired impulse response sequence of the filter. So if we take inverse Fourier transform of hd of e raised to j omega, we can get hd of n. That is, the samples hd of n can be determined by taking inverse Fourier transform of hd of e raised to j omega. That is, hd of n is equal to 1 by 2 pi integration of hd of e raised to j omega into e raised to j omega n d omega from minus pi to plus pi. Let us call this as equation 2. This impulse response that we have determined here is an infinite duration sequence. For implementation of a digital filter, hd of n should be a finite sequence. The impulse response obtained from equation 2 is an infinite duration sequence. For FIR filters, we truncate this infinite impulse response to a finite duration sequence. Of length n, where n is odd. Truncated HD of n is called as h of n, that is h of n equal to HD of n for n equal to minus n minus 1 by 2 to plus n minus 1 by 2. Defining Hn of z as z of h of n, that is z transform of h of n, and knowing by definition Hn of z equal to summation from n equal to minus n minus 1 by 2 to plus n minus 1 by 2 of the product of h of n and z raised to minus n. Since in Hn of z we are having summation from negative value of n to positive value of n, this Hn of z represents a transfer function of non-causal filter. So we have to convert this transfer function into a transfer function of causal filter so that we can implement it or realize it. The transfer function Hn of z represents non-causal filter. Hence, the transfer function of equation, let us call this as equation 3 here, of equation 3 is multiplied by z raised to minus of n minus 1 by 2. Therefore, Hn of z equal to z raised to minus of n minus 1 by 2 into summation of h of n into z raised to minus n from n equal to minus of n minus 1 by 2 to plus of n minus 1 by 2. Simplifying, we get h of z equal to z raised to minus of n minus 1 by 2 into h of 0 plus summation from n equal to 1 to plus n minus 1 by 2 h of n into z raised to n plus z raised to minus n. Due to truncation of Fourier series, oscillations are found in the frequency response in the passband as well as in the stopband. These oscillations are because of the slow convergence of the Fourier series, particularly near the points of discontinuity. This effect is known as Gibbs phenomenon. So we'll just write the definition of Gibbs phenomenon here. Fourier series results in oscillations in the passband and stopband. These oscillations are due to slow convergence of Fourier series particularly near the points of discontinuity. This effect is known as Gibbs phenomenon. The undesirable oscillations can be reduced by multiplying the desired impulse response by an appropriate window function. Now we'll take one problem on designing FIR filter using Fourier series method, and after that we will see what is a window function and how the window functions are used in designing FIR filter to reduce Gibbs phenomenon. So now a problem on design of FIR filter using Fourier series. Design a FIR low pass filter with cutoff frequency of 1 kHz and sampling frequency of 4 kHz with 11 samples using Fourier series method. Determine the frequency response and verify the design by sketching the magnitude response. Solution. Given Fc equal to 1 kHz and sampling frequency Fs equal to 4 kHz. Therefore, omega c is equal to analog frequency omega c into capital T, or that is equal to omega c into 1 by Fs, that is 2 pi into 1 into 10 raised to 3 divided by 4000, which simplifies to 0.5 pi radian per sample. The desired frequency response HD of e raised to j omega of low pass filter is HD of e raised to j omega equal to 1 for omega greater than or equal to minus omega c and less than or equal to plus omega c, and equal to 0 for omega greater than or equal to minus pi to minus omega c, and omega greater than or equal to omega c to less than or equal to pi. And the same thing you can see here now. From minus pi to minus omega c, that is in this range, HD of e raised to j omega is 0. And also from plus omega c to plus pi, HD of e raised to j omega is equal to 0. Whereas for omega between minus omega c and plus omega c, HD of e raised to j omega is equal to 1. Now we have to make use of Fourier inverse transform to find HD of n. Using Fourier inverse transform, HD of n equal to 1 by 2 pi into integration of HD of e raised to j omega into e raised to j omega n d omega between the limits minus omega c to plus omega c. That is 1 by 2 pi integration from minus 0.5 pi to plus 0.5 pi one into e raised to j omega n d omega, that is equal to 1 by 2 pi integration of e raised to j omega n with respect to d omega is e raised to j omega n by jn, that is e raised to j omega n upon jn. Limits of integration are minus 0.5 pi to plus 0.5 pi. One by pi into n inside the bracket e raised to j 0.5 pi n minus e raised to minus j 0.5 pi n divided by 2j, and this bracket may be now written as sine of 0.5 pi n. That is equal to 1 by pi n into sine of 0.5 pi n, and this holds good for all n except n equal to 0. To find HD of 0, that is HD of n for n equal to 0, we have to go back to the Fourier inverse transform first step, and there we have to place n equal to 0 in e raised to j omega n. HD of 0 equal to 1 by 2 pi from minus omega c to plus omega c 1 into e raised to 0 d omega. That becomes 1 by 2 pi into omega with limits of integration from which becomes equal to 1 by 2 pi into omega, and taking lower limit as minus 0.5 pi because minus omega c is equal to minus 0.5 pi and upper limit omega c equal to 0.5 pi, we get 1 by 2 pi equal to 0.5 pi. Minus of minus will become plus 0.5 pi. 0.5 pi plus 0.5 pi will become 1 pi. Pi will cancel. We'll get this HD of 0 as 0.5. Now we will calculate HD of n for n equal to minus of n minus 1 by 2 to plus of n minus 1 by 2. Given n equal to 11, therefore minus of n minus 1 by 2 is equal to minus 5 and plus of n minus 1 by 2 is equal to, and plus n minus 1 by 2 is equal to plus 5. So now we have to find HD of n for n value varying from minus 5 to plus 5. Therefore, for n equal to minus 5 to plus 5, HD of n will become h of n because we are going for truncation here. So h of n may be now written as 1 by pi n into sine of 0.5 pi n. H of 1 equal to 1 by pi into sine of 0.5 into pi into 180 by pi into 1, because we have to convert here radians into degree. 0, because sine of 180 is 0. Similarly, we have to find h of n value for n equal to 2, 3, 4 and so on up to 5. So we get h of 3 equal to minus 0.1061, h of 4 equal to 0 and h of 5 equal to 0.0637. And we know that for FIR filter, h of n is equal to h of minus n. Therefore, h of minus 5 is equal to h of 5, that is equal to 0.0637. H of minus 4 equal to h of plus 4, that is equal to 0. H of minus 3 equal to h of plus 3, that is equal to minus 0.1061. H of minus 2 equal to h of minus 2 equal to h of plus 2, that is equal to 0. H of minus 1 equal to h of plus 1, that is equal to 0.3183. Because we have learned that for linear phase filters, h of n is equal to h of minus n. Now we can write for the transfer function of digital filter, that is h of z. The transfer function h of z of digital low pass filter the transfer function of, now you can write the transfer function h of z of digital low pass filter by taking z transform of h of n and multiplying it by z raised to minus of n minus 1 by 2, that is h of z equal to z raised to minus of n minus 1 by 2 into the summation of product h of n into z raised to minus n from n equal to minus of n minus 1 by 2 to plus n minus 1 by 2. N minus 1 by 2 is 5, therefore z raised to minus 5 into summation from n equal to minus 5 to plus 5 h of n into z raised to minus n. That is z raised to minus 5 into h of 1 into z raised to minus n. In expanded form, it may be written as here. Further simplifying, we can write h of z equal to h of 0 into z raised to minus 5 plus h of 1 into z raised to minus 4 plus z raised to minus 6 plus h of 2 into z raised to minus 3 plus z raised to minus 7 plus h of 3 into z raised to minus 2 plus z raised to minus 8 plus h of 4 into z raised to minus 1 plus z raised to minus 9. Now substituting for h of 0, h of 1, h of 2, h of 3 and h of 4, we get 0.5 into z raised to minus 5 plus 0.3183 into z raised to minus 4 plus z raised to minus 6 plus 0 plus minus 0.1061 into z raised to minus 2 plus z raised to minus 8 plus 0.06 37 into z raised to 0. Z raised to 0 means 1. So 1 plus z raised to minus 10. Plus h of 5 into z raised to 0 plus z raised to 10. And the frequency response may be found by substituting for z equal to e raised to j omega in h of z. That is, h of e raised to j omega is equal to h of z at z equal to e raised to j omega. Hence, we can write h of e raised to j omega equal to 0.5 into z raised to minus 5 plus 0.3183 into z raised to minus 4 plus z raised to minus 6 minus 0.1061 into z raised to minus 3 plus z raised to minus 8 plus 0.0637 into z raised to zero plus z raised to minus 10. At z equal to e raised to j omega. That is equal to 0.5 into e raised to minus j 5 omega plus 0.3183 into e raised to minus j4 omega plus e raised to minus j6 omega minus 0.1061 into e raised to minus 3j omega plus e raised to minus j8 omega plus e raised to minus j8 omega plus 0.0637 into e raised to 0 plus e raised to minus j 10 omega. Now writing these exponents which are in the form of e raised to j theta in rectangular form, we get now we will separate out cos terms and sine terms. Next we have to find amplitude of h of e raised to j omega. Which is under root real part square plus imaginary part square. And real part and imaginary parts here are to be evaluated for different omega value. Say omega starting from 0 to pi radians per sample. The calculation made for magnitude of h of e raised to j omega for omega varying from 0 to pi are tabulated here. You can refer, but it is very much essential that you calculate the values on your own using calculator. I will scroll slowly for your reference after calculations. Now you can see the frequency response graph. On y-axis we have taken magnitude and on x-axis we have taken digital frequency. By calculation we have seen that at omega c equal to 0.5 pi, the magnitude is equal to 0.5. And also you can observe here the oscillations in the magnitude in passband as well as in stop band, and this is what we call as is Gibbs phenomenon. In order to reduce these oscillations, we will have to make use of windows, which we will take up in next class. I will stop the class here. Thank you.